So you have these right. So you have these multiple implicit fields defined like this. The way we assemble all of these fields, let's say you have 5 different fields defined on different types of skeletal elements, let's say a point and a line segment and so on and so forth. You could do a very simple blending operation on them. It's known as summation blending. And by just adding those implicit functions, you get the final implicit function f that gives you a shape, the implicit function of a shape that you wanted to model. So this is modeling using skeletal elements in the implicit form. And have an example. Okay, I have some couple of examples coming up, but this is the nature of the implicit function. Sorry, the fall off filter. And you can see that on the x-axis, I have the distance values going from 0 to whatever distance values. And then the field value is on the y-axis. And the nature of this fall off filter function is such that it converts an increasing distance field value to a decreasing field value, right? So for example, the zero distance value is mapped to 1, and then the increasing distance values are smoothly tapered down until it either goes to 0 if it's a finite support fall off filter function, or to very small value if it's an infinite support function. And most of these are, I believe, finite support functions. And these are some of the well-known fall off filter functions: Blin, Metabol, Soft Objects, and Wyville. These are, some of the most widely used fall off filters, right? The job is simple. It converts a distance field which increases from the skeletal element to, it could increase to infinity actually. It converts that into a decreasing field function, right? And this is how the shapes look like. And these are, the top row shows implicit functions for 2-point skeletals. So 2 points. A point will have a implicit field that looks like a sphere, right? And remember, we are doing summation blending. We are just adding these up. So in this equation, fxy equals to summation of all fi's. We are just adding these implicit functions together. So what happens is that the field also gets distorted once they're added together, right? So look at the blobby, look at the first column first. And as you go down that first column, you will notice that when I bring these point skeletons together and take a iso contour of it just to visualize how the particular surface looks like, and it could be a level set k, not necessarily 0, because or it could, well, yeah, because we have already applied the filter of function. I'm actually interested in the 0 level set here. So you will notice that as I bring these point skeletons together, the spheres seem to be getting merged together, right? Initially by touching each other, and then gradually mixing up into each other, and then eventually becoming a bigger sphere from a blobby object, right? The behavior is the same across all, but then with different fall-off filter functions, when it becomes and how when it merges with the other implicit function, and how much shape distortion happens is slightly different. Like you can see in this figure that the onset of this joining of these two spheres is at different times, right? For example, if you notice, soft objects and Wyville do not merge until the until the second stage. But then, you know, eventually they'll all will become a single object once the uh, point skeletons are at the same point in space, right? So that's just to show the differences between these four fall-off filter functions, right? So I'll come back to this one in a moment, but I wanted to show you, you know, this right-hand side. You see this hand image, and it's a very well-known hand image because it shows how you could use these um, skeletal elements to model the hand. And remember, this goes back to 1991 when sophisticated modeling techniques did not exist. Today, we have a lot of tools at our disposal to model both real life and synthesized objects. But that point of time, it was a great feat because nobody had modeled the hand like this one. This was considered to be an achievement at that point of time. So you could see that a lot of details have been tried to model here, but the basic elements are the same. It has skeletal elements that are line segments and points. And then instead of summation blending, it uses what is known as convolution surface, right? Just to avoid some problem with summation blending. We'll come back to that in a moment. So that is the kind of surface modeling that we can do with this, and much more, right? So anyway, let's move ahead now. Before I move on, let me quickly talk about continuity and gradient. And I believe you have already seen some of it in previous lectures, but just to recap, C0 continuity ensures no jump in the function. And so if you don't want any jump in the function, you want to make sure that your function is at least C0 continuous, right? If it has jumps, then it is C minus 1, right? So C0 will have creases in it, right? And usually anything more than C1 or C2 is what we would want to prefer. One of the properties of 3D scalar fields or any implicit function is that you can calculate the gradient at any point, and this gradient is basically perpendicular to the surfaces that you are modeling, to the surface that you're modeling. So let's say you took a zero level set from the implicit function, and you wanted the normal vectors. And remember, normal vectors may be needed for a lot of things that you want to do. For example, if I want to display a implicit function, right? For the simple display, right? You can see that it has a very nice lighting and shading, right? You see these two dots, and immediately the human eye says that, aha, there are two light sources somewhere, and the light is shining on these balls, the spheres. And then the brightness also tapers off, and it becomes darker toward these edges of the projection of this sphere. This gives us an illusion that it's a shining object, right? And how does the computer know that it has to display a shining object, right? So we take cues from physics, and in the physics of computer rendering, you need normal vectors to figure out how much to shade at a point, right? So that's one reason why you need normal vectors. So if you ever want to compute normal vectors in for an implicit function or implicit surface, calculate its gradient. And how is the gradient? How do you calculate the gradient? The gradient is given by del f by del x, del f by del y, and del f by del z. It's a vector. So when I ask you, give me the normal vector at that point, you quickly calculate the gradient and normalize it. Remember, normal vectors must always be normalized. Okay, normals have to be normalized. So normals are sort of unit vectors. So you normalize it, and there you go. You get the perpendicular vectors, right? And to be a little more precise, let me quickly talk about the normal vector, and then do we have a question here? I think we have some questions here. No, not yet. But maybe because I'm not monitoring the chat box, so it's best to speak up and quickly interrupt me speaking. So, right. So when I talk about the normal vector, what do I really mean? Being perpendicular to a surface. So let's say that's your surface. That's your surface, let's say, right? And I'm talking about this point P here. When I say that a vector, a normal vector n hat is perpendicular to the surface, what I mean is that it is perpendicular to the tangent plane at same point, right? So if this is my tangent plane pi, and a tangent plane is by nature tangential to the surface at that point P, right? And therefore this vector n is perpendicular to this tangent plane, right? And for any shape, different points every point will have its own tangent plane. In this 2D diagram, I'm drawing these tangent planes by tangent lines, but the idea is the same, is that you have one normal vector here, and if I pick another point, let's say this point, it will have its own tangent vector. This point will have its own tangent vector, and then you sort of have a normal at that point, right? So you could pick any point and then be able to calculate the normal vector at that point by just taking the gradient of a implicit function. Is that point clear to everyone? Right? It's a very useful idea of computing normal vector at any point in the implicit field. Okay, so right, so what can we say about the function from its given gradient? If the gradient is C naught, right? Let's say the gradient has only C naught, is only C naught, then we could say that the function f, the implicit function f, is C1, right? And it basically says that the normal varies smoothly and the surface is C1. Okay, everybody understands C naught, C1 continuity, right? Here. Any quick question about C naught, C1? So C1 says that first derivative exists everywhere on the function. C2 says the second derivative exists. C0 says that not the first derivative doesn't exist, but there is only it's only continuous. It's not smooth, right? And this is pointwise. So at all points on the surface, this has to happen. Okay, so let's come to distance field now. We have been talking about distance fields a lot, right? So what is a distance field? Okay, Vignesh is saying something. What is the notation C naught about? Like, is it some space being represented? A C naught just says continuity 0. So C0 continuity. Okay, it's just a notation. So C0 says 0 derivative or no derivative exists. And C1 says first derivative. So you can differentiate it once, but you can't differentiate it twice, the second derivative.
There's no background required for understanding that C naught, C1 apart from this.
Basic calculus, yeah, is what you need.
No, in calculus this is a standard representation you're seeing. Like,
yeah, that's the same representation.
Okay.
Right. So so a distance field with respect to a geometric object T, right? So given a geometric object T, and now I'm not only talking about skeletons, like we said, skeletal modeling, but I can even go one step further and say that, look, I can have any arbitrary geometric object, T, any shape, and I can define a distance field on that shape. So a distance field F defined on the shape T at a point P in this space is given by the shortest distance to the shape. So basically, if you read the right hand side, it is minimized. It is the minimum distance between Q and P, where Q is a point on the surface, right? So in layman language, for any point P in space, I pick the point on the shape which is closest to it, and the distance between those two is the distance that I pick. And it so happens that that distance is the perpendicular distance for if it's a smooth object, right? So FTP is the shortest distance from P to T in that sense. And T could be any geometric entity embedded in 3D or 2D. It could be a point, a curve, or a solid, right? So that's my distance. That's my definition of distance field. And just to give you an idea how it looks like, you can see this image here, and whatever you so you see some blue region, a white region, and a red region. The white is not actually a region, but it's just it's a curve, and that's my shape. So my shape T is essentially this curve here. And maybe I can also scribble here. I think it. Okay, no, not really. So this white curve that you see is my shape, and you will be able to then see that the inside of that is all blue, the outside is all red, and these are distances, increasing distances. The darker the color is, the higher, the more is the distance. The distance increases, right? And if you talk in terms of a differential equation, it's the Kernel equation that governs the computation of a distance field. Oh, okay, I think I can. Just no, I didn't want that. Anyway, right. So maybe I can. Distance fields are very important. Let me just again discuss that a bit more. Right. So you have a shape, a closed shape, let's say, and you calculate the shortest distance from a point, and I already had discussed with you earlier, the shortest distance is going to be the perpendicular distance, D. Once you calculate this distance, you will notice that these distances will increase, and they will form structures like, they will form mountain structures like mountains, right? So what is the structure of a mountain? The mountain has a peak, and then it has points, it has ridges. So it also has these points that are local maxima, right? So for example, I'll draw here in this diagram, you will see that what I'm drawing in red here is sort of the local peak, and let me also erase some part of it, and then create a protrusion here. So what happens is that as a response, this is going to change a little bit. Right. So that's the highest point right? That is to say that any point on this local maxima will be furthest from its boundary, right? Of course, there is this global maxima sitting here that has the highest distance, and actually this skeleton is not completely okay because I erased it. But then, let's assume this skeleton is correct. Uh, you will observe, and you must have observed also in that diagram, that the highest colors were at this maxima, right? Similarly, outside also, you're going to have something similar, the highest points, but in the other direction. So what we usually do is that, because distance is always positive, we usually indicate that, let's say, the interior distances are positive, the outside distances are negative. And when you assign a sign to the distance field, it becomes what is known as a signed distance field, or in short known as SDF. Okay, so if I represent an object, if I want to represent a shape in the form of an SDF, it has a negative, it has a positive area, and then the object from which I computed the distance field itself sits at the zero level set. So if f x y is my distance field here, which is, by the way, a implicit function, right? Because for every point I'm storing a value, the value happens to be distance value here, right? So my object S shape is basically just like before. It is the set of all the points for which fxy equals to 0, right? Do you guys realize that? Because remember, the distance at the object boundary is 0. So any distance over here at these points is exactly 0, all 0, right? So it satisfies the property of the implicit shape representation, that set of all the points for which fxy equals to some scalar k, which in this case equals to 0, right? And we have a positive and a negative because we assigned a sign to the distance field, right? So a distance field is just a special case of my implicit, it's a special type of implicit function that stores a distance uh, for every point. And which distance is it? It is the shortest distance measured from the object's boundary, right? Right? And anytime I want the object boundary, I could do a polygonization, which we will discuss toward the end of this lecture. Anytime I want an explicit representation, let's say I want the bunny mesh back from this shape, from this implicit shape. What I need to do is just get the level set, and a polygonization is just a level set calculation method, right? It uses some algorithms. Similar to, for example, like the marching cubes algorithm, to get the shape back. All right. Any questions on distance field? Okay, and while we are at the find distance field, let me also tell you that the equation governing the distance field is the so-called Kernel equation. And the Kernel equation doesn't really care about the sign, because if you remember, it says norm of, so what does it say? So f is my, and let me fix my notation quickly. This is f, right? So it says norm of the gradient is 1. So what does it mean, norm of the gradient is 1? What is f? F is my implicit function. So what is grad f? Grad f is del f by del x comma del f by del y. That's my gradient, right? So what Kernel equation says is that the norm of the gradient, and what is norm of the gradient? Norm of the gradient is del f by del x whole square plus del f by del y whole square equals to 1. Well, I just squared it, right? So that's what it says. And think about it for a moment. Why should that happen? This is the property of distance fields. Property of distance field is that the norm of the gradient at every point is equal to 1. It's a very strong and a very interesting property. And I can draw it for you here in this diagram as well, right? So let me try to draw it for you. So let's say we have a point here, and let's say that there is a distance field defined. The gradient of the remember we took the distance which is normal to the boundary, the shortest distance. So the shortest distance then accordingly says that the normal vector, well, the normal vector has points always perpendicular to the level sets, and in this case it's going to be something like this, or the direction can reverse if you want, but this is fine, right? Let's say this is grad f. If I'm here, if I'm at a different point here, my grad f will be like this. And here, for example, grad f will be like this, right? You got the idea. If I'm outside here, grad f will be like this. It's always perpendicular to the boundary. It changes. But what the Kernel equation says is that the gradient, the norm of the gradient is 1. That is, wherever the gradient points to, its magnitude is always 1. And why is the magnitude 1? Is because I am computing distances. If it was something else other than the distance, then it could have been not 1, but because the fact is that I'm computing distances, that is a unit change a unit change away from the boundary will lead to a unit change in the distance value, right? If I'm x away from the boundary, x distance away from the boundary, then the f equals to x, well, the magnitude, right? This is right, not the magnitude. It is correct. If I'm x distance away from the boundary, the value of f, if f is x, right? So measuring along the normal direction, the magnitude is always always 1, right? In other terms, physically, if I do a physical interpretation of this statement, it says that, let's say the distance field is a mountain on which you are walking up or down. If you walk along the normal direction, you will always experience a slope of 45 degrees, right? And that's the highest slope ever you will encounter in a distance field. So if you are walking on a mountain of distance field, the maximum slope that you will encounter will be 45 degrees, which, by the way, is not an easy slope to walk along. Any other direction will always have a slope less than 45 degrees. Okay, so that's a fundamental property of distance field, is that the magnitude of the gradient is always 1.
Sir, I didn't was not able to quite relate like why only 45 degree, why not more than that?
Why not anything else? That's what I
Hmm.
explained here. So you walk a unit distance away from the surface. What will be the value of okay, maybe I can try once more. Let me try once more. Okay, so let's consider a point P here. Okay, for this point P, what's the normal direction? The normal direction is, oh, not this, not this. The normal direction is probably the, oops. So that's my point, and that's my normal direction. Let's say this is perpendicular. Okay, now tell me, if I walk x units along this normal vector. So this is a normal vector. I walk x units further away what will be the distance value?
X.
It will be x, right? So if you
Yes.
take a directional, if you calculate the magnitude, it's equal to x, you just said,
X.
because I'm moving
Yes.
in this direction, right? So if that's my normal vector, this is my normal vector, its magnitude has to be x because I have moved that direction. And you know what you could do as another aid is take a cross section along the normal. Let's say that's my cross section which I'm going to draw. I'm going to um, cut this distance field along this line, and that's the line. That's my 0. Excuse me. That's minus d. That's plus d. Minus d plus d. If I plot it, what do you get if you plot it? So get a plot like this, and that's my distance field, and that's the distance x that I'm moving away from it. So that's how the distance field will look like, isn't it? In a as a cross section of this along this direction, right? So because I moved the same distance, I moved distance x, and I calculated distance, so that's the value of the distance field. This is a change of h in along x resulted in a change of x in the distance field, and therefore this is 45 degrees. Does it make sense now?